Okay, so the second main part of this module is this idea of using Matlab to find residues and poles of S-domain functions. And Matlab has this wonderful built-in utility or function called residue, which allows us to take an S-domain function, define it as the ratio of two polynomial expressions, and determine both the residues and the poles at one point. And so when we have complex conjugate poles associated with complex conjugate residues, this formula is a very handy one to use, where we take the combine these two complex conjugate poles to create a single shifted cosine, where the frequency of the cosine is given by the imaginary part of the pole. The real exponential has this rate of decay, which is given by the real part of the pole, and both the magnitude of this time domain function and the shift are given by the residue, A, which is in general a complex number. So if we consider how to find the inverse transform of, say, this example, we can use this concept of this function residue. Residue returns both the residues and the poles of this S-domain function. And we pass to the residue function the numerator polynomial, which in this case is 5, and the denominator polynomial, where we have 7s cubed, 31s squared, 46s, and 24. And so if we see what that gives us, we see that we get 3 poles, which we would expect, given the fact that we have this third-order polynomial in the denominator. And we have this complex conjugate poles and the associated complex conjugate residues. And so if we want to calculate the inverse transform in terms of a shifted cosine, we can take the absolute value of r and multiply it by 2. This is the, so this 1.58 is now going to be the value or the size of this shifted cosine. And then the angle of r we can calculate. Now the angle r returns a value in radians, so if we convert into degrees, it makes it, we can see the answer in degrees. So what we find is that the time domain function is made up of two signals. One is a real decaying exponential, that's this -2, and the other is this shifted cosine, which is caused by this complex conjugate poles. And so the decaying exponential has a magnitude of 0.83, and the shifted cosine has a magnitude of 1.58. It has a decaying exponential in front of it with this rate of 1.21, and the cosine has a frequency given by 0.49 and a shift of minus 121 or 122 degrees. So to find the shift, what we do is we look at the residue, which is associated with the pole which has the positive imaginary part. So this is the residue number 2, so we look at the angle for residue number 2. So if we go back, this I of t, quite quickly we found, has this inverse Fourier or inverse Laplace transform. And so with relative ease, compared to the work that needed with partial fraction expansion, we can find these residues and these poles. So the second part of this is to actually make use of this to determine how the resistance of the inductor for this circuit that was given in application exercise number 1 can change the values of the poles. And so since we have this characteristic equation given by this, where our A is related to A and B are related to these quantities in terms of the circuit, what we can do is we can calculate A and B for a range of RL. And so these are vectors. So if I define a vector for RL, say with 1,000 points, then A and B will be vectors with 1,000 points, 1 point for every value of RL. And then I can use residues to calculate the residues and poles that are associated with this differential equation. And so you first need to find the S-domain expression for your output voltage, and then define that as a S-domain expression in your residue function, and calculate these R and P for every value of this A and B. So it would be exactly the same thing, except here you could put this in a for loop and have calculate the value of R and P for each value of your A and B. So your A and B would enter into the vector for the denominator, and of course you'd have a vector for the numerator as well, and then you can calculate your R and P for this given range. So if you do that, you should find something that looks like this, where you have the real part of the poles. So here there's 4 poles, so so since our V of S is given as this cosine, this V of S provides 2 poles to the output, and the transfer function, or since it's a second order circuit, they provide the other 2 poles. So we get these 4 poles that exist due to this V out or VO of S. So we find we get these 2 poles, or these 4 poles, and as R varies from 0 or 1,000 to 10,000, we can see how the real part of these poles changes. And so for pole number 4, you can see the real part is always 0. For pole number 4 and 3, they're overlapping, and the real part is always 0. And then pole 1 and 2, they overlap for this first part, and then at this point, just over 6,000, they begin to split off. And if we look at the imaginary part of the poles, which is the interesting thing, we can see that pole 3 and 4 are complex conjugates of each other. Remember, they have no real part, but now they're complex conjugates plus and minus 100J. So poles 3 and 4 represent a perfect cosine with no decaying exponential, and they don't change. They don't change at all as RL changes. And the reason for this is because these are the forced poles. These are the poles due to the cosine which is given. So the cosine contributes these poles to the output. And then pole 1 and 2, which are due to the differential equation and due to these coefficients A and B, you can see that pole 1 and 2 are complex conjugates of each other again at every value of RL. They're plus minus J. And we get to this point, just over 6,000, where the imaginary part is 0. And so at that same point, the real parts split off. They're no longer equal. And the imaginary part becomes 0. So we can interpret this in the sense that if RL is less than 6,000, then the time domain waveform will be made up of a cosine with frequency 1,000 or 100, and there'll be another cosine that has a frequency depending on what the value of RL is. For example, if the value of RL is 2000, then the frequency of the other cosine is 300 rads per second. So we can, by changing RL, we can change the output. And on the other side of things, as RL is greater than 6000 at this point on, then the output will have the cosine due to the input, this 100 rads per second cosine, and then there'd be no imaginary part for the other part of the response, so you would only have these two decaying exponentials. So in the module, what you're asked for is to identify what range of RL would you get these two cosines. One is due to the source and one is a variable frequency cosine with a decaying exponential. So if you look at these plots, when our RL is less than this value, which turns out to be about 6,290, and you can see this by just zooming in. So just about this 6,290, we see that the below that we'll get these two cosines. So RL is less than 6,290. On the other side of it, as RL is greater than 6,290, then we'll have the cosine due to the input source, and then the two decaying exponentials with alpha 1 and alpha 2 given as the real part of the poles. So this would be alpha 1 and alpha 2, alpha 1 and alpha 2, as we increase the value of RL. So it's quite interesting. Very simply, in Matlab, you can see that that you can change this response by just adjusting what your RL is. Now, if you're looking for RL to be produce a specific response, so let's say minus 212 and 476, then we can go back to us, and what we're looking for is 212, so we want something in this range. So right about here, the real part is minus 212, so say this is 6,820. And let's see if this produces the correct 6,820. So this is about minus 476, which is what we're looking for. And the residues can be found by looking at how R changes with this RL. So we can look at the real part and the imaginary part of the residues and consider that when the resistance is 6,820, one residue is minus 0.8, and the other residue is about 3.44. So we have this 3.44 and this minus 0.8 as a result. So this seems to be the right value of RL. And similarly, we could look for the same thing and see how the value for RL for the second case.